Hello, everyone, and welcome back for the next session of the 2022 Flight Software Workshop. Our next presenter on the agenda is Ehsan Salehi of LDRA, presenting testing techniques for safety and secure avionics software. Ehsan, it's all yours.
Thank you. I'm going to share my screen. Hello, everyone. My name is Ehsan Salehi, one of the field application engineers for LDRA. In this presentation, I'll be talking about the testing techniques, methods, and for safety and secure avionics software. The agenda for our today's talk is testing safety and secure coding, structural coverage, different techniques of testing, and conclusion at the end. So start with the testing safety and secure coding. For the testing, the role of the software testing is in the security and safety-oriented software development process involves with two related topics: functional testing and risk-based testing. Functional testing is meant to ensure that the software behaves as it should. Therefore, it's largely based on the software requirements, and analogously, risk-based testing is based on the software risk, and each test is intended to probe a specific risk that was previously identified through the risk analysis. So you can see the V model that is used for safety testing. Requirement can be written into the number of different programs. For example, DOORS, Polarian, JAMA, even Word and Excel. These requirements can be then automatically parsed and brought into the tools such as LDRA tool suite, as you can see on the screen. This particular tool then allows us to see the up and downstream traceability between the system's high-level and low-level requirements. And then user can see the mapping between the requirements and the source code. As you can see here, we mentioned that you should be writing both functional requirements and secure requirements to make sure that you have the full traceability mapping throughout the ML. The use of the automated tool dramatically reduced the administrative overhead associated with the bi-directional traceability. Here we see a low-level requirement mapped to the source code associated with the requirement, the tests associated with the source code, the status of those tests, and the artifacts generated by any of those tests are being marked as completed. There's a green check mark next to the left of every one of those test cases. The ability to regress the completed test makes it easy to confirm the functionality remains the following modification elsewhere. So when doing our functional testing, we must make sure that we are covering all of the codes and ensuring that there is no code we have not tested. There are different ways to look at the coverage of the code. Two of the most important ones are the statement coverage and the branch cover. As you can see in the lower section of the screen, structural coverage is quite often mandated by many of the industry standards. For avionic, DO17DA B and C is a well-known standard that is calling for structural coverage. And the measure of structural coverage can change, depends on the design assurance level. So now we are going to move on to the structural coverage, which is the heavy part of our talk here. Structural coverage defined as how much of the code is covered by the executing test. Structural coverage will help to understand if the code is written as it's behaved and exists as it's intended from the requirements and not just by the source codes. In the next following slides, we will see how to measure and what are the types of the structural coverage. So it's obvious the purpose of the testing and verification is to make sure we are satisfying the requirements. So the structural coverage can help us how much of the testing is enough. And not only because it's mandated by the standard, but it's also helped to improve the quality of the software. When running our test, the result can be viewed through the use of the structural coverage. We can look at the entry and exit points, the functions and procedures, and etc. On the screen, and now we have a flow graph showing that what section of the particular function have been covered. And just behind it, we have our industry standards requirements for meeting the structural code coverage. The green in the flow graph represents of the code which has actually been executed and therefore covered. However, the red part is not. Does the red part, which is not being covered, means the code is unreachable or unreachable? Is it a dead code? Is it an infinite loop? Is our testing correctly designed to satisfy the requirements for our system? This is why the functional testing and measuring the structural coverage becomes important. It's easy to spot the part of the code that are not being tested, but if they haven't been tested, why? These are the questions a verification engineer would ask. Either the test needs to be more robust, they are not quite satisfying the requirements, or the code needs to be removed because there is no requirement for it, or we have to add more requirements to generate more test cases. The coverage can be represented in a number of different ways, including the qualitative summaries as illustrated in the top part of the slides here. So we can see the reports here where for a specific source code or even for procedures, how much coverage we have. And then we can look at it in the flow graph, which is produced by the LDRA TB Vision tool to show what part of the codes have been covered and whatnot. So if you're looking at the structural coverage, the most common part of the structural coverage are statements and branch cover. But for more critical projects, there are more type of structural coverage are designed to satisfy the requirements. For example, modified condition and decision coverage or MCDC, and also object code coverage are being called for DO178C DAL-A. These coverage needs to be taken from the tests that are actually executed on the targets. So now we can look at to see how much and how we can get those coverage. We can get the structural coverage by designing the system testing or unit testing. System testing is where the application is executed and exercised with many combination of the inputs. So the software can be producing and be executed in an environment where you can inject some inputs and get the output out. The entire system, the entire software can be tested with the system testing. However, unit testing would be creating an isolated harness around a specific part of the software. It either can be one source code or one CSCI, can be one function, or can be multiple source codes or multiple functions to be brought into the harness, and then generating the test cases just to satisfy the procedure-based testing and also the low-level requirement associated with those procedure testing. Here you can see the different types of the reports that can be generated as a result of the system testing. This is a dynamic report generated by the TB Vision from the LDRA tool suite. You can see the set, how much coverage we have for a set. We can also see the source codes. You can also see from the procedure perspectives how procedures are being covered as a result of our testing. If there are no branches, the analysis, the static analysis part of the tool should be able to determine that there are no branches, and if there are, or same with the MCDC. So that helps us to measure our structural coverage and see how much of the requirements have been satisfied by our testing. You can also see the flow graph again, on the procedure view to see what part of the codes have been missed or not been covered as a part of the either system testing or unit testing. The important part is either unit testing or system testing have to be executed on targets. So unit testing or low-level testing can be used to test each and every function, or just to test the part of the code that the system test didn't execute. Basically, user can exercise the unit testing either for robustness or to get or cover the missing coverage gap as a result of not having enough conditions in the system level testing, or it's not be able to generate test cases on a specific scenarios. But again, the unit testing needs to be run on the target, and the harness needs to be able to generate an executable, can be loaded on a target, be able to generate the results from the target, and then connected back to the host computer. So any tool, any measuring coverage tool can analyze the coverage and see if the test cases have been enough, if the results are passed, and satisfy the requirement. Once the system testing and the unit testing are executed, the coverage, the results of the coverage from these two needs to be combined, so we can get the better view of how much of the entire system have been covered. You can see the combined coverage report here being shown by our dynamic analysis coverage with LDRA tool suite. Now we're going to move on to different testing techniques. So now, so far we're understanding the requirement-based testing is very important, especially when you are dealing with the software that are associated with the life of people. There are numerous ways of tester can use to generate test cases. And here we're going to just focus on the test part, not the requirement-based testing, and try to introduce you, or if you know already, how you can actually achieve these type of testing. We have a equivalence class and input partition testing. We have analysis of boundary values testing, error guessing, error seeding, interface test, fuzz injection test, and or fault injection test and fuzz testing. For the equivalent class partitioning, this technique basically use the possible value and divide it into the different sections. One section would be the other or the lower part of the boundary condition where it's not actually valid data. Then one part would be the valid data, that is the nominal range. And also we have the upper level of the boundary where the data can get invalid. In this case, if you are testing some characters between 0 to 9, anything that is below 0 are invalid. Anything is above 9 are also invalid, and the valid value is only between 0 to 9. The divided sets are called equivalence partition or equivalence classes. Then we can pick only one value from each partition and for the testing. So the idea behind this is if one of these values in each one of these boundaries are failing, then the entire values can be also subjected to a failure. And else where if basically the invalid part of the partitions are showing as expected, then everything else is also satisfied, and so on. For the boundary values, the process of testing also needs to test the higher and lower extreme. So you can look at the class partitioning, but you also need to add what is the lowest value can ever be received by the procedure, and what would be the highest value can ever be possible to be sent to the procedures and to our test. So we have extra boundaries, as you can say, speaking. The error guessing is an interesting one. It's based on the experience. Usually, this method of testing is used in the production lines or by the accepted test procedures. Experienced engineer who has been used the software or the device, and he knows what are the most critical area, can design test cases to make sure those critical part of the software are passing. So error guessing has no explicit rules for testing. The test cases are designed depend on the situation, either drawing from a functional requirements when an unexpected or undocumented error is found while the testing is in operation. The error seeding is also interesting. In the error seeding test, developer, usually that actually also happens before the formal qualification testing and in the dry run. Developer inject some errors to the code. And the goal here is the tester who is independent than developer. And we have to make sure the separation of tester and engineer or developers are respected here. And the tester is supposed to figure out those errors. The idea is if the more of the known errors have been found, the more percentage of the software has been tested. Fault injection technique is for improving coverage by tests by introducing fault to a test case path. In particular, it's targeting the error handling path that might be otherwise rarely be followed. It's often used with the stress testing and is widely considered to be an important part of the development for the robust test testing. Fuzz testing is an automated software testing technique that involves providing invalid, unexpected, and random data as an input to a computer program. The program is then monitored for exceptions such as crashes or failures and built-in code assertions, or for finding potential memory leaks. Typically, fuzzers are used to test programs that take structured inputs. The structures is specified, for example, in a file format or a protocol, or in the distinguish valid from invalid inputs. An effective fuzz generate semi-valid inputs that are basically valid enough so that they are not directly rejected from the parser, but able to exercise interesting behaviors deeper in the program, and also invalid enough so that they might stress different corner cases and expose errors in the parser. Tools such as LDRA can have an options or what called extreme testing. Extreme testing can generate this random data or fuzz testing. Here is an example of show how TB Extreme or extreme testing component of the LDRA tool suite can be configured to a subject code to a range of appropriate tests. And then the test get generated by our tabular extreme test, and user can actually link them back to the requirements or study them and basically evaluate them from their own test cases to see the missing gaps, and if they want to, they can import those test cases to their own created test cases to satisfy the low-level requirement. So to summarize, the validation and verification role in the Avionic is different than just the environments when development of the product does not interact and deal with the life of the people. For this reason, the testing will be a very important part of the software development lifecycle. Each type of testing will be used to serve the purpose. Robustness, in addition to the required testing, can help to improve the quality. And finally, validation and verification can be costly, but it is important when you're dealing with the safety and security environments. Thank you so much for listening to my presentation. If you have any questions, be happy to answer them.
Thank you so much. Ehsan, looks like we do have about 5 minutes for some questions. We'll give
Sure.
some time for some of those to filter in. While we're waiting, I'll also highlight, Ehsan, thank you so much, especially for your 3 other presentations that are pre-recorded and already linked up on our website.
Sure.
Some amazing work sharing with the workshop audience this year.
Thank you. Thank you for having us.